So we are part of the LED task force, and we are going to be discussing our LED luminous intensity measurement methodology. It's been challenging, but we think we're honing in on a solution. So I'm going to let so these are some of the key people in our LED task force: Anatoly Zakharov, myself, April Fisher, John Lewis, and Long Legion. And Long, if you want to take it away with our presentation overview.
Sure. Thanks, April. So today we're going to talk about the luminous intensity measurement methodology. And although the spec has been there for a while, we do have in the spec a specific range, but there has been a lot of work behind the scene, and that's where we are today to update you on where we're at. So let's talk about the current spec, what we have in the spec today, and Anatoly, and April, and John will follow up with the what we've been doing. April will talk about the sensors and the probe that we have chosen, and John will talk about the test fixture and the next steps. And then we'll follow up with the Q&A after that. So the current OCP 3.0 spec today, if you look in the spec, I believe it's in, I think section chapter 4 maybe, or table 40. It does talk about the specification for the link and activity LEDs. And if the board has room for the LED, what the current spec is saying is that for the green LEDs, it has to have a dominant wavelength between 513 and 537 nanometers. And for the amber, it should be between 580 and 589. So the green LED is typically for the activity. The amber or yellow LED is typically for the link. You notice that the wavelength specified here is a bit shorter or narrower range than the typical LED range for green and yellow. But this is what we have today in the spec. The specification, the purpose of this presentation is to talk about the luminosity. So the current spec we have, the numbers that we have is at the surface of the LED on the bracket, the luminance across the surface area should be between 12 and 18 MCD. And so that has been there since, I think, earlier version of the spec, but we are working to we are working to put a more achievable range in the spec, hopefully in the next release of the spec. Okay. And then we also come up with a methodology that we'll be presenting today so that we can have a consistent measurement across products, across companies. So with that, Anatoly, go ahead with your next slide.
Hello. So luminous intensity challenges. First, we had as a LED vendor data sheet versus actual measurements. First unknown was at the test that how LED vendors do measure their LEDs brightness for their data sheet. For example, do they include luminous intensity and the flux into their data sheets? All first attempts to correlate measurements from datasheet with actual LED measurements were with a huge offset for luminous intensity. And that's how that all development has started. So tools ability to measure LED brightness and its luminous intensity with the spec within the spec showed that instruments and tools are available for brightness measurements, but most of them are designed to measure LED brightness for light fixtures in the room or in appliance. And wavelength measurement accuracy versus luminous intensity accuracy become significant in a difference for wavelength was easy measured by modern tools like spectrum analyzer, and luminous intensity become difficult to measure because all measurements become relative, and tests showed that even a spectrum analyzer was unable to measure LED which are dim or LED with light pipes at front of them. That led to the further analysis of LED shapes, sizes, lenses, angles, apertures, reflections from the faceplates, and light pipes properties and their design. As you can see on the picture, we can see that LED has additional properties as a luminous flux and luminous intensity. And on the bottom of the screen, you can see LED types and their shapes. They're not uniformed, so therefore they will produce different lights properties, and sensor will pick up those differences as well and will determine that measurements for you in a different way, which you have to account for. That brought to the next phase as necessity of development of the LED fixture and to development with controlled voltage, current, and resistance to drive LED to establish a baseline for measurements between vendor samples and measurements at Intel lab. Sensor probe selections and alignment with LED fixture. And research showed that with experimentation on LED fixture, that sensors probe selection with their necessary mechanical and optical alignment is a very important aspect prior to any measurements on LEDs. Measurement uniformity across all LED types and NIC configuration showed that with some observation, it had some signified differences on green and amber LEDs as a uniformity. And at same level of millicandela, LED behave a little bit different, and to establish that difference, more further research was required, and uniformity become necessary to continue to investigate and apply more different calculations, more accurate configurations and calculations in order to meet that uniformity across different LEDs and NICs. And those challenges requested some trend to broaden spec range. For example, when you do measurements with the LEDs, you could see that there is very significant parameters where LED become from batch to batch with different variations, and that variations do affect your measurements in the final conclusion for how your spec will accept those measurements or not. And that phase brought us to certain probe selections and sensors, which April will talk about, and how to calculate them.
Thanks, Anatoly. So after quite a bit of trial and error by Anatoly, he found that the best probe sensor solution out there that we could find was from a company called Optimistic Products. And how they work is they have a sensor that's connected to a fiber optic probe, and that fiber optic probe is used to measure or to go right against the LED. So we are currently looking at the Spectre sensor, and the Spectre sensor is able to measure both wavelength and luminous intensity, which are two important parts of our specification. And the way that it measures it is it outputs a voltage. You can see the pins on the end of the sensor picture there. And so you measure an analog voltage coming out of that. And then you can cross-reference that with a chart. And the wavelength, the chart is provided, and you don't need to worry about sensor to sensor variation. The luminous intensity, however, each sensor and fiber optic probe and LED combination, especially the sensor and the fiber optic probe, you do need to worry about a certain amount of calibration. So that's something that our LED task force is investigating. But basically what that means is you can see the graph all the way on the right. There's a slope for this line where you are correlating your voltage out and your luminous intensity. And that slope is going to change slightly depending on your sensor and fiber optic probe combination. So as we're developing all of our methodology and our test fixtures, we are taking that into account. And we're going to be working, well, I'll let John talk more about that, but we are going to be working on making sure that that is accommodated for. So something else that we want to emphasize, a lot of times when you're measuring luminous intensity, you're measuring at LED level. Well, it's not really what we're looking for. We're wanting it to be NIC level. So as you can see in the picture bottom left, that's the picture of the fiber optic probe, and it's going to be measured right at the faceplate is what our methodology is recommending. So again, NIC level, not LED level. So we're going to have to be taking into account light pipes and faceplate and all these different things that are going to interfere potentially with the light coming directly from the LED. And with that, I will hand it over to John Lewis to talk more about how we're integrating this sensor probe combination into a test fixture.
Thanks, April. So the LED group decided that we wanted to create a test fixture to standardize this. It goes with the earlier presentations that you've heard, and so they'll volunteer to contribute something to the community. And what we've decided to do is use the Spectre probe that Anatoly and April and others had recommended, and simply put an ADC and a micro and go to USB. This is the same MCU that's used on the existing thermal test fixture. The USB powers the device and the probe, and so it's very self-contained. And the ADC is capable of the accuracy that's listed there, the 3 nanometer accuracy on the color and the 3 millicandela on the luminous intensity. One thing we did add that's not hasn't been discussed much is we did add a temperature sensor in case the during our development of the methodology, if the temperature makes a significant difference to the measurement being recorded. And so on the next slide, we'll see a picture of the first board. This is not something that we're going to contribute. It has big screw terminals there to check on the power draw to make sure that USB can handle it. There was some question about that given the micro and the sensor and the ADC. And so this is a board that we have in our lab today. The PWB, and what we're showing, thanks to the Intel ME team and Jonathan, we have a just kind of a mock-up of a screw fixture that would allow for precise replication of testing. And the test fixture that it's connected to is actually the thermal test fixture. And that would hold the card rigidly, provide power and PCIe, so you would have a complete system there capable of adjusting the card as necessary. Then you can see a top view down, but the, kind of the milling machine positioning circuit there, or fixture would allow you to keep the probe perpendicular to the faceplate, which is critical, as April mentioned. And then with some calibration, it would allow you to repeat the procedure on multiple cards very quickly and easily. As far as the test fixture goes, it's very simple. It's in the lab now. The code is being worked on. We expect to ship these to our small subgroup this week, and they will be contributed before the end of the year and likely be available to the community early next year. Next slide, please, April. So what are the next steps? Well, we need multiple companies to analyze the probes. I know we're just getting our probes set up, so we will be replicating a lot of the work that Anatoly has done. We need to complete the test fixture development. I've gone over some of that, but it is looking good. Right now we're developing a calibration fixture, and which is holding a known good LED and a known value for the wavelength and luminous intensity from an LED manufacturer. And then the group will determine the methodology for calibrating the fixtures. And this will be done by, for instance, UNHIOL. Before you ever purchase a fixture, it will come pre-calibrated. And then we need to determine the extended luminous intensity range. We have several things that outstanding. One is the distance from the LED. Again, April said we're trying to do this from a NIC perspective and not an LED perspective. As the LED is moved away from the faceplate, it's going to dramatically reduce the effectiveness of the LED and the measurements. What are the ambient lighting requirements, if any? How much is ambient light causing a problem with the measurements or a differentiation in the measurements? We have two different LED types or light indicator types. One is a light pipe and the other is the bare LED. And it may be that those require different ranges to get the same user impact. And then we're going to look at the temperature and see if it is impactful. And if so, we have the capability on the test fixture to record the temperature at the same time that the luminous intensity and wavelength are measured. And then we'll be working in the NIC-MES subgroup to update the specification with the recommendations from the group and based on the work done here. So as I mentioned, the LED test fixture is expected to be available in Q1 of next year. You're going to be able to purchase that on UNHIOL's website. And if you don't want to do that, the full design package will be up on the wiki, as it is with all of the test fixtures that have been contributed. And then we really encourage all interested parties to join the mailing list and participate. This group moves forward fastest when everyone participates, and we look forward to working with you on this.
All right. Thanks, April, John, Long, and Anatoly. That wraps up that session. So I believe